Okay, so trying to pack this full of movies, I had to cut like 5 things I wanted to talk about. But we've heard a lot about large scales and galaxy scales. I know that's what most of the people in this room care about. But I really care about, I know some of you do too, the connections between the small scales and the large scales. And I know we all know these problems are intrinsically extremely multi-scale, but a classic example is all this black hole discussion. You're strongly coupling scales from the event horizon at order AU to order megaparsec scales for black hole feedback in the CGM. And again, we've known this for decades. This is highlighted in things like radio jets, but it's also highlighted in things like the discussion about little red dots. We're talking about cosmological formation mechanisms, but also how to explain their spectra on scales of the true accretion disk. So, this is a problem a lot of people have been interested, including myself, for a long time. It spans a huge range of scales, and our traditional approach is kind of illustrated here, showing, our list of arbitrary names for how we cut the scales. And what we do is essentially stitch models together, whether those models are analytic or simulation. People simulate some very finite range of scales and then, essentially attach them, whether you call it a subgrid model or a prescription, or you machine learn on smaller scale simulations to represent hyper resolution in larger scale simulations. We're simulating these scales independently. And we all know, or we should know, that this is formally justified if there is an explicit strict scale separation in your problem, and there's definitely not one in this problem, basically. There is no actual line that divides the torus from the black hole radius of influence from the bulge, for example, where we can just say, these physics don't talk to each other. That's what makes it hard, but also interesting and active as a field. So we've been trying to push on this, and I want to highlight work by a number of collaborators: Jonathan Mercedes-Feliz, Rachel Cochran, working with Daniel Ingles-Alcazar, and a student at Caltech, Jayden Bardati, doing sort of cosmological zoom-ins following inflows further and further. Daniel did some of the first work, sort of following inflows from cosmological scales to scales of order a parsec around the black hole, and showing that you could get large inflow rates. And this is closely related to the discussions we were just having about sort of how you get down to maybe a little red dot scale cluster or galaxy at order hundreds of parsecs. But we wanted to keep pushing further, but this has involved a lot of work with myself, Mike Grudich, and a number of other collaborators in what we're now calling our Forged in Fire project, because it doesn't just require pushing to higher resolution, it requires involving more and more new physics as you push to those scales, because you cannot make the same physics approximations that we all make in our galaxy formation simulations on scales of order 10 Schwarzschild radii around the black hole. You will just get wildly wrong answers that won't make any physical sense. And vice versa. There's plenty of things that nobody in the accretion disk community doing traditional accretion disk simulations in the central 100 gravitational radii around the black hole bothers with things like self-gravity and star formation and stellar feedback and protostellar jets and things like that. So this has involved sort of linking our Starforge project, resolving individual stars, with our FIRE project and a lot of other physics to sort of cover this range. And this is a movie illustrating the first of the simulations from this Forged of Fire project, where we zoom in from a cosmological simulation and we keep following and refining the gas all the way down. This initial simulation went down to about a few hundred Schwarzschild radii. I'll show you in a moment simulations that go down basically to the horizon. And we can really resolve, this is the real accretion disk that's actually forming in the simulation, not just some analytic representation of the accretion disk on much larger scales. And we can learn a lot from these kinds of approaches, not just for calibrating our subgrid models, but new physics as well. So what we see is, as you zoom in, you get all sorts of different structure. You can see in this particular case, this is at redshift 4.5 in a massive starburst galaxy, a giant clump of gas gets sort of tidally disrupted around a pre-existing black hole and gets wrapped up and forms the accretion disk that funnels in gas at a quasar level accretion rate here. And Nick Kaz extended these simulations down to event horizon scales with GRMHD to see the formation of jets. And I'll touch back on that. But one of the things we got out of this, we expected this would inform our understanding of quasar fueling, but one thing we genuinely didn't expect was some really surprising new physics of accretion disks that only came out precisely because we did the multi-scale problem and didn't just make the usual boundary condition assumptions. And that was that these accretion disks are incredibly strongly magnetized compared to what traditional accretion disk models predict. What do I mean by incredibly strongly magnetized? Well, in a Shakur-Sunyaev accretion disk model, the ratio of thermal pressure to magnetic pressure is typically about 100 to 1, 100 times the thermal pressure compared to the magnetic pressure. And in these disks, the thermal pressure is not bigger than the magnetic pressure by a factor of 100. It's smaller than the magnetic pressure by a factor of 10,000. So it flipped by a factor of 1,000,000 in the opposite direction. And that completely changes a lot of our intuition about these accretion disks. And basically what happens is, this is sort of zooming in, showing what dominates the pressure on different scales. As you get to smaller scales, you'll see the whole movie turn red. This is also just an excuse to show another pretty movie before the coffee break. Basically, as this cloud gets wrapped up around the accretion disk and tidally disrupted, it has sort of normal magnetic fields for a GMC complex, but those fields get tidally stretched in the toroidal direction as this wraps up and winds around the black hole. And that provides resistance against the vertical collapse of the accretion disk. So actually, the interesting thing is this disk becomes supermagnetically dominated, not by having stronger magnetic fields. In fact, the magnetic fields are slightly weaker than in a traditional Shakura-Sunyaev disk. It's because the magnetic fields prevent the thermal pressure from getting enormous, which is what happens in a Shakura-Sunyaev disk, because the disk collapses to an incredibly razor-thin configuration, basically. Shakura-Sunyaev disks at high accretion rates, this is a known problem for many decades, are incredibly thin. H over R is like 0.001. This causes all sorts of problems for modeling spectra of quasars and other things. For example, Martin referred to the fact that, accretion disks need to be externally illuminated. That doesn't work in the traditional Shakura-Sunyaev model. And there's a lot of other things that this can do. If you care about AGN, I'm happy to talk more about this, but just to give an example, this is what happens if we turn off the magnetic fields on the left. This is the density profile of the disk. It becomes razor thin. It effectively collapses to our resolution limit in the vertical direction, versus when we have magnetic fields, you see this very thick vertical structure. And this has an enormous effect on what's happening around the disk. So basically, the magnetic pressure can support, through a combination of actually vertically supporting it and boosting Q, but also through stronger magnetic torques that funnel the gas through more efficiently. You get about 1,000 times higher accretion rate in the magnetized case compared to the unmagnetized case. You also get that the star formation rate inside the accretion disk, which is this blue line, is suppressed by a factor of 100,000 in the magnetized run compared to when we turn off. Basically, what happens when we turn off magnetic fields is that the whole disk just boom, turns into stars and fragments. And this is, again, an old problem. Jeremy Goodman was writing papers about this 30 years ago saying we can't fuel a quasar because the disk will just fragment catastrophically into stars and nothing will ever get through. And that's exactly what we see if we don't include these very strong magnetic fields. Now, here's the one slide. I made the mistake of putting little red dots in my talk, but I'm actually going to talk about little red dots. With a former student who's now at CETA, Yanlong Shi, and Kyle Kremer, who's at UCSD. We've been looking at the implications of this for IMVHs and little red dots. This was actually from some simulations Yanlong originally ran in 2020 that we wish we'd analyzed and made predictions from then to actually predict. But basically what he found was we were interested to pick up from where all these other talks left off. We've got some seed black holes in a dense cloud of gas, and we want to ask, can they really accrete? Because I think, much like Guillermo alluded to, that the hardest part for understanding little red dots is actually understanding their spectra. And do these models actually work to explain these weird spectra? And that's what we're trying to see. Basically, if you start from a normal cloud, the cloud just blows itself up very quickly and you don't get much growth onto black holes. That's good because we don't see a bunch of IMVHs running around normal star clusters. But if you start from a sufficiently dense and massive star cluster, it's been known for a long time in the star formation literature that you have a sufficiently high surface density cloud, it runs away and turns almost all of its mass into stars. You get a very high star formation efficiency and you form a bound star cluster. Your black hole seeds, 1 in 10 to 100 of them gets lucky if they're solar mass seeds and lands in a dense clump of gas and can start accreting. You get a sort of winner's win runaway where that thing starts gobbling more and more up and gets very quickly moved to the center of the cluster by dynamics. And the protobulge or protocluster, whatever you want to call it, anchors that black hole. It develops one of these hypermagnetized disks in Yanlong's simulations, and it has an envelope at about 10,000 gravitational radii that has the right density and temperature for these sort of envelope models. Now, Yanlong and Jaden are both doing subsequent zoom-ins to go all the way to really resolve the broadline region of these things so that we can make, and Jaden is doing a full radiative transfer to see, can we really get the right spectra? I wish I had a spectrum to show you. We're not quite there yet, but I think we're going to be able to start pressuring these models soon. And we're also starting to zoom back out from these. So we all know we love AGN feedback and we need it. I'm going to insist that we all love it, even if you don't. So with Hung-Yi Su and others, we've started zooming back out from these simulations to make more self-consistent predictions for things like jets and feedback. And he's also been working with Karen Cho at the Black Hole Initiative, and we're also working with Minghao Guo at Princeton on parallel approaches for doing this. Hiren and Minghao are more focused on sort of your M87 radio mode type galaxies and massive ellipticals. We're a little more focused on quasars. It's just more an accident of what physics are in our codes that make them better able to handle those situations. But also Nick Kaz has been looking at these jets and actually has a really cool result, which is that we get a jet that dies and we actually get a radio quiet quasar, which is, I think, the first time a GRMHD simulation has actually produced a radio quiet object as compared to a radio loud object, which is what they always get, basically. It has to do with the environment around the black hole. Nadine Solomon's been looking at some of the radiation pressure-driven winds, and I'll just completely side note advertise another fun AU scale phenomenon that she saw is around black holes and stars. You can get magnetogenesis cosmologically from radiation pressure on dust grains, which are charged, driving strong currents in the early galaxies. And Yanlong and Jonathan and Rachel have been looking at the effects of the galactic winds, zooming back out. Jonathan has several recent papers on this. Another student, Sam Panada, has been looking at the effects of the magnetic fields in cosmic rays. So let's jump back out, since I know you do all care about large scales, and mention a few slides about cosmic rays very quickly on larger scales. So we can zoom back out. The magnetic fields on very large scales seem to have a fairly weak effect, but the cosmic rays can have a pretty strong effect on these scales. Now, the challenge with cosmic rays is understanding the transport physics, which again relates to sort of AU scale physics. Whether cosmic rays fling out of a galaxy barely interacting at all, or whether they're tightly confined and build up an enormous pressure and do a lot of work on the gas, has to do with magnetic field fluctuations on about 0.1 AU scales, which are what determine whether those cosmic rays get bottled up and trapped on magnetic field lines or not. And we don't understand those at all. You think it's bad for your subgrid models for galaxy formation. I can give you 6 models just by Alex Lazarian that, if I extrapolate them to the CGM, differ by about 10 orders of magnitude in the predicted diffusion coefficient of cosmic rays in the CGM. So this is going to be an empirical problem that we have to solve by calibration to different observations. Now, there's beautiful observations in the solar system and very near it of cosmic rays, and you start by calibrating your model to all of that, just like we always do. You calibrate to the best studied systems. But that's the solar system, so it's only one place in time. We can then expand to other places in the galaxy. So with Margot Fitzaxon, we started looking at molecular clouds in different galactic environments and in the Magellanic Clouds. And a student, Isabel Sands, has started making gamma ray maps. Also, if you're interested in the galactic center excess, I can talk to you about Isabel's work on that. She's seeing Fermi bubbles and really modeling their full gamma ray spectra in these simulations, self-consistently for the first time, and modeling the galactic gamma ray environment. And we know that once these cosmic rays escape to the CGM, they can do a lot. So Irina Butsky, Soching Ji, and many others, and other groups as well, have shown a sort of consistent result, which I think actually most of the galaxy community now agrees on, which is that in a halo where cosmic rays do nothing, Milky Way mass galaxies tend to have a lot of hot gas and a lot of inflow at large radii. But if you do build up a cosmic ray pressure-dominated CGM, you tend to support a lot more cool gas in the halo, and you tend to have a lot more slow, coherent, gently accelerated outflows. And I think that statement is not very controversial. The question is, which regime does nature actually prefer? And the problem is, again, this uncertainty in the microphysical scattering rate in the CGM is the dominant uncertainty here, because couple of allowed models. One is I take my ISM calibrated scattering rate and assume it's just a universal constant. Then I get, you plug that in, you get that the transport equations have some simple solution. You get that the cosmic ray pressure declines relatively slowly away from the galaxy as you go further out into the CGM, which means that your cosmic ray pressure stays high while your gas pressure drops more rapidly, which means you inevitably get a cosmic ray pressure dominated CGM. Of course, it's also perfectly plausible that I say, outside of the ISM, my scattering rate, this purple line, plummets. The turbulence is too weak, the magnetic fields are too weak, I'm not able to generate these small scale fluctuations efficiently, and therefore I don't confine the cosmic rays, they start to essentially free stream out, and so I don't build up any pressure in the CGM, and they basically don't talk to the gas on their way out. That's also perfectly allowed. We're playing around with peng-O on a calculation. There is a weird side effect of that. You actually assume they all escape. You get the answer that the IGM has about 100 times the cosmic ray pressure as it has thermal pressure, which really seems like it should mess with the forest and other things like that. But then again, it depends on how well coupled they are. If they are completely decoupled, then they just don't do anything, right? So it's like a neutrino background. So it comes down to this uncertainty. So the question is that we've been thinking about more lately, can we really directly constrain this part of the equation? Since that's really the determining factor about whether we care about cosmic rays for feedback or not. Whether you care about it from AGN or whether you care about it from supernovae, it's really about can they build up pressure at these large radii in the CGM. So in particular, we've been working on this with a group of 3 students, Isabel Sanz and Sam Panada, whom I mentioned, as well as Emily Silich, who's an observational X-ray and radio astronomer at Caltech, who's been collaborating with us, and we just put in a number of proposals to follow this up. The idea is basically, can we test these different cosmic ray pressure profiles that you might get from different transport models? So the simplest place to start is with Milky Way-like galaxies, because there we know the rate at which cosmic rays are leaking into the CGM. Remember, we live in the burbs of the Milky Way. We're practically outside of the galaxy already. So the local cosmic ray measurements are very much telling us the rate at which cosmic rays are escaping from the galaxy. You can infer this quite robustly from those local cosmic ray data. We can also basically measure the speed at which they're bulk streaming out of the galaxy. It's order 100 kilometers a second. I'm just rounding to a nice round number here for everybody, but that's sort of the average bulk speed that they're escaping out of the galaxy at about 10 kiloparsecs to the center. So let's take as our starting point the most naive possible model, which is we know the rate at which they're leaking out of the center. We'll assume it's nice and spherically symmetric. Losses are very weak in the CGM because there's not a lot of gas for them to collide with. And we'll assume they just drift out at constant velocity. Then you just get a wind solution, basically. They're just streaming out at constant velocity. It's pretty trivial what your prediction for the pressure is. And you can ask, where would we observe this? Could we observe it in synchrotron? That's where we often look for cosmic rays. Well, the problem is synchrotron involves this nasty convolution with the magnetic field. And at high frequencies, this effectively goes like B to the 4th or so, which is really bad because we don't know what B is in the CGM. It's also just way too low surface brightness for existing radio probes. So that said, there's still a lot of synchrotron you can do. Sam Panada has a series of papers looking at in the ISM of nearby galaxies. You can probe different transport physics. You can get qualitatively different shapes. These are synchrotron maps with different cosmic ray transport model assumptions, and we can really start to break some degeneracies here. And you can probe the very inner CGM with these, when people in the synchrotron community say they detect a halo around an external galaxy, they usually mean like 1 to 3 kiloparsecs above the disk, basically. So for many people in this room, that would be maybe the disk halo interface or something like that. Definitely not 100 kpc, but there's a lot of information there. So we shouldn't neglect it, but it's not going to get us to 100 kpc. What about gamma rays? That's another place we always look. Well, it's a little cleaner. It's just the product of the cosmic ray density times the gas density gives you pion production rates that give you so there's still a degeneracy with the gas density, which for a lot of galaxies, you don't know the gas density at large radii. But it's also super faint by gamma ray standards. And it's also unresolved for almost any galaxy because you got to remember Fermi's got like a degree beam. So it's really hard to resolve these things, even on scales of 100 kpc. And we originally wrote this paper and we're like, this is hopeless because if there's a Milky Way mass galaxy further than a megaparsec, you'll never detect it. And literally, it was Isabel and Sam in our group meeting were like, aren't there 2 Milky Way mass galaxies within a megaparsec of us? And yes, there are. So it turns out the Milky Way and M31 both have extended gamma ray halos that are detected out into their CGMs. And those are the profiles, the boxes and points. And these are the vanilla model, just taking the gas density profiles from other sources, our best estimates of the gas density of the halos. This is what you predict for their gamma ray halos. So encouraging that this really naive model seems to work there. But there's one more signature that we can look for, which is, I think, not been thought about nearly as much, which is in the X-rays. So in X-rays, you get inverse Compton scattering. And this is normally thought of as a very high energy process. But the thing to remember is for cosmic rays escaping the ISM, almost all of the energy is at sort of 0.1 to 1 GeV, especially once it propagates to those large distances. And those inverse Compton scatter a CMB photon to about 1 keV. So this is actually a soft X-ray signature that you look for. And since it's scattering off the CMB, the inverse Compton X-ray luminosity is the product of the cosmic ray energy density, which is exactly what we want to measure, times the number of CMB photons. But we know this number. This is one of the best measured numbers in astrophysics, right? Perhaps the best measured number in astrophysics. So if we measure this, we get a very clean constraint on this. So the model prediction from these really naive models is this for these different mass halos for different mass galaxies, where the different lines are just slightly different variations of the model, but they basically follow the same trend. And it turns out there is a claim of a measurement of a soft 1 keV diffuse halo around Milky Way mass galaxies out to 100 or 200 kiloparsecs. So E Rosita detects soft X-ray emission, and with the same color code, these are the E Rosita detections. And again, there's no like fitting here. This is just really that dumb model, like 100 kilometers a second, same injection rate as the Milky Way. And it's bang on there. And there's also now several papers, including one by Emily Silich that just came out, showing that this emission at these very large radii cannot be thermal without breaking something deeply fundamental. If you assume this is thermal emission from hot gas, which is what they've generally been interpreted as in these models, there's some nice papers from CAMELS, for example, that show the only way in all the survey of all the simulations that CAMELS has in its library, the way CAMELS fits this is it moves all the Milky Way mass galaxies, stellar mass galaxies, into 10 to the 13.5 solar mass halos, because it needs that many baryons to reproduce this signal at large R. There just aren't enough baryons to do it otherwise. There's also problems with the metal budget, the feedback budget. There's a host of other reasons why this can't be thermal emission, and I'm happy to talk more offline about that. So it's very natural, on the other hand, if it's cosmic rays. And there was just a paper by Samuel Liu showing this for some fire galaxies. So this is the halo luminosity outside of 50 kiloparsecs. And this is what we get from just thermal emission in our thermal dominated CGM simulations, the hotter simulations that don't have cosmic rays. And this is the 1 keV X-ray emission in the cosmic ray dominated halos. And the thing to remember is those have cooler gas in their halos. So you get this very counterintuitive answer that cosmic ray dominated halos are cooler, but they look hotter by any traditional X-ray metric at least. So they can be very tricksy. I was sure when we started this paper with Sam, the whole point was we were going to rule out the cosmic ray dominated halos because they're cooler, so they produce less thermal X-rays. So we were going to be able to conclusively say from the E Rosita data that model was dead. And in fact, instead we ended up favoring the exact opposite of what we originally expected. Lastly, I'll just throw it out there and come talk to me if you're interested. I have a tinfoil idea that this might also be really messing with our idea of what's happening in cool core clusters, because AGN radio sources can really boost the KeV continuum in the same way around strong radio galaxies. And I think this can explain some very weird things otherwise about cool cores. But I will end there. Thank you very much.
Thank you, Phil. All right, one question before the break.
Thank you. Very exciting talk. So about this X-ray emission,
Yeah.
the inverse confidence is very exciting. I think if that model is correct, you do not expect thermal SZ effect, do you?
Yes. So one of the predictions is that you'd get a deficit between the, what you would assume from the X-rays if it were thermal emission compared to the true SZ signal, which would be still a robust indicator of the true thermal pressure. And there would be a difference between those at these scales. Now, we don't really have that for L-star galaxies. There is a tentative sample, and this is actually what Emily just led the proposal with some high-resolution radio instruments like Mustang. She's got some early results on a small sample of cool core clusters that appear to show this deficit in the SZ in their central regions, which is very exciting. Those are bright enough that you can do this. If you're aware of ways to do this at sort of 100 kpc in Milky Way mass halos, let me know. I don't know of a data set that does that. Yeah, I thought those were more like a megaparsec naively, but maybe, well, we should talk more. Yeah.
Okay, I'm going to encourage people who have more questions for Phil to ask him questions over a coffee break. And I'm going to also suggest that we come back at 4:40. So give ourselves a little time here to actually have coffee. All right. Thanks, everybody.
Thank you, Jenny. Oh, yes.